So I'm recording right now. Which pair has 0 or infinite solutions? Well, we could just put them all in Desmos and take a look. So we're going to put them in one by one. So 4x minus 2y is negative 2. The next one, 5x plus 3y is negative 4. And then the last one, 8x minus 4y is negative 4. Okay. So if you saw what was happening there, you will notice that the blue line just got overlapped by the purple line. So that means that the blue line and the purple line are actually the same line. And if they're the same line and you're wondering how many points they're touching at, the answer is all of them, or infinity points. So they don't just cross each other at one point, they cross each other at infinity points, which means the number of solutions between the blue and the purple is actually infinite. So if we go back to the question, we could say that B and D are the same line. So B and D have infinite solutions. If we go back to Desmos, we can see that there are no lines that are parallel. I think I did not properly do this example. I didn't make it up properly. And I did not come up with any pairs that had parallel lines. Okay, so the green and the red are close to parallel, but I do not see a pair of parallel lines here at all. So what we would do is go back here and we would say there are no pairs that have 0 solutions. So in Desmos, what about the other lines? So the red one and the blue one have a solution here, one solution. The green one and the blue one have a solution here where they intersect. And then the red and the green actually have a solution here. Okay, so all the other pairs of lines have one solution. It's just like the blue and the purple one are exactly the same line, so they have infinite. So what I've done here is I've just rearranged each equation so that I can read the slopes, y equals mx plus b. So the slope of A is negative 2, according to the rearranged form. The slope of B is 2. So they are not the same. They're not parallel. I can also do the rearrangement for part C, which will have 3y is equal to negative 5x minus 4. And I can divide everything by 3. So you can see that this one has a slope of negative 5/3. So that's still not the same. And if we keep going, we can also do part D. I'm running out of colors here. I guess I'll do that one in green as well. So for part D, I can rearrange that one. And I'm going to get negative 4y is equal to negative 8x minus 4. Divide everything by negative 4. So then y is equal to 2x plus 1. So let's take a look at the slopes. This slope matches this one. This slope doesn't match with anybody. Does that mean that part B and part D are parallel? Well, if you notice that the y-intercept also matches, not only are they parallel, but they are the exact same line in y equals mx plus b, which is the exact same thing that Desmos told us. So B and D are the same line. You can see it on a graph. You can see it by equation. There are an infinite number of solutions between B and D, and nobody else is parallel. We are asked to solve this by substitution, and the multiple choice question might ask what other equations must be solved. So a student has suggested that we isolate y in the bottom equation first. If we do that, then we're going to have negative y is equal to negative 1 minus x, but we don't like negative y, so we're going to multiply this side by negative 1 and that side by negative 1. So I'm going to end up with x plus 1. So if you wanted to do this, you sure could put it back into this equation. Instead of writing y here, you could write this. And that's the whole idea behind substitution. We're substituting this for that. So we could do that. Equals 2. So this is an equation that might have to be solved. Okay, so this might show up in your multiple choice. But then again, maybe not if somebody else chose to isolate a different variable first. Like, let's say that you chose to isolate x first. So x is equal to y minus 1. So if we move the y to the other side, we're going to get positive y. So then we could substitute this in for this x. So maybe then we write an equation that looks like this with only y's in it. And then we might have to solve that equation, right? And furthermore, that's not the only strategy we could do. What if somebody decided to isolate this y first? So negative y is equal to 2 minus 3x. And I don't like negative y, so I'm going to go negative or positive 3x minus 2. So then we could take this expression and put it in for the bottom y down here. So we would have x minus 3x minus 2 equals negative 1. And so depending on which color of root you decide to take, the equation that you have to solve partway through the process ends up looking a little bit different. So if this is a multiple choice question and your version is not showing up in the multiple choice, maybe you need to understand that there's more than one way to do this, and you need to work out a different way to do it. Okay? Furthermore, if you don't see any of these options, well, maybe what if they isolated this x first? I would not recommend it, but they could. And if they did do that, what would that look like? Okay. And if you still don't see your answer on the list, what you might have to do is simplify a little bit. For example, if I distribute this out through here, that's still the same equation. It just looks a little bit different. So one way to do is to run through all the scenarios. Another way to do it that you can maybe eliminate some of your options is if you try all the equations they give you and figure out what answers they're going to give, see if it matches the answers that you would have gotten either through Desmos or solving however you would have done. And if you realize that some of them are going to lead to an x that doesn't match, then you know that that's an incorrect equation. So the deeper understanding is no matter how you do it, when you solve for x, you solve for y, you'd better be getting the right answer. So we're asked to solve for x in this example. One student has suggested that we distribute, which is a good idea because right now we don't like having brackets. It just makes things very difficult to work with. So I'm going to expand out the brackets and then I'll make a decision of whether I want to do it by substitution or elimination. So I'll expand this out to get 2x plus 4 plus y is equal to 8. Okay. So then you can clean it up even a little bit more, and you should, so that you don't have different constants and different x terms and different y terms. This is a lot cleaner. I've got one copy of x, one copy of y, and one constant. So I can work with that. Okay. Then I can do it to this one as well. So then we have 7x minus 2y plus 6 plus 24 is equal to 0. And again, I don't want to have two copies of things. So 7x minus 2y plus 30 is equal to 0. So a student has suggested that at this point, we're going to do an elimination. So we're going to try and eliminate our y term just so that we can solve for x, right? So if the question's only asking for x, they don't even need you to solve for y, then why don't we kill y? Because then we don't even need to solve for it later. So if we multiply this equation by negative 2, or positive 2, let's say, then we're going to get 4x plus 2y equals 8. And then we'll sneak the green equation underneath it. We'll line it up all nice. Oh, wait a second. The green equation looks like this. So can I just continue like this, or does something have to be done? So the problem right now is that our constants are on different sides and they don't line up. So there was a little bit of a debate among the students on whether we should move the 8 over here or this to the right. It turns out it doesn't matter which one you do, but you have to do one of them. Okay, if you don't do it, then they don't line up and you cannot eliminate. So just for the sake of it looking nice, I'm going to move the 30 over to the right, which turns it into negative 30. And now our equal signs are lined up and we can go ahead and do our elimination. So these happen to eliminate and we can add these together. So 11x is equal to 8 minus 30, which is negative 22. Divide both sides by 11. It turns out x is equal to negative 2. Okay, and we did not have to find y because it just told us to solve for x, so we're done with this. I have some equations with some gaps in them, and I want to know what conditions would give zero or infinite solutions. So a student was pointing out that infinite solutions mean that the lines have to be the same. And because they're in the same format, then you would say that to make it the same then, that A would have to be 6, B would have to be 5, and C would have to be 10. That's how it has to be for it to be infinite solutions. So that's true. That's correct. But what about zero solutions? How would we tackle that one? So in order to determine if they have the same slope, we do have to convert them into slope-intercept form. Okay. So if I take the first one, I'm going to try and isolate for y. So I'll have 5y is equal to negative ax plus 10. And then I divide by 5 like this, and I'll have y is equal to negative a over 5 x plus 2. And I can do the same thing with this equation. So I can go by is equal to negative 6x plus c, and I can divide this by b. So you just go through with it like it doesn't even matter that there's no numbers there. So 6 over b is x, and c over b is 2. Oh, sorry, c over b is there. Okay. So this is the first equation in this nice format, and here's the second equation. So in order for them to have zero solutions, they must be parallel lines, which means that this slope over here had better be equal to this slope over here. So we would say that this has to be equal to that. Now, in this case, we are not able to get a real answer like 2, 6, or 5, or a is 8, because we have two variables. We can't solve this. The only thing that we can say is that this thing better be equal to this thing. So that's our first condition. A student pointed out that if you want there to be zero solutions, your y-intercepts better not be the same. Because if they're the same slope and the same intercept, they're the same line, and you're going to have infinite solutions. So what we're also saying is that this thing, this y-intercept here, better not be equal to 2, right? Otherwise, then we're going to have the exact same line. So in this case, the infinite solution is pretty easy. We can just come up with numbers, but the zero solution is a little bit harder. There's actually two conditions that have to be met in order for these lines to be parallel. Okay. So a student has requested that I write out a final answer. So in this case, my final answer is that for there to be infinite solutions, then A has to be 6, B has to be 5, and C has to be 10. That's it. But for there to be zero solutions, then negative A over 5 has to be equal to negative 6 over B. And actually, I could remove the negative and it would still be okay. Okay. And then C, I would put also C cannot be 2. So let me just clean that up a little bit since it is my final answer. You can remove the negative from both sides. So these are the conditions that have to be met to have zero solutions. And these are the conditions that have to be met to have infinite solutions. In your example on the actual mini assignment, I believe that there are more variables even than I have. I think there's actually 4 variables. So under your infinite solutions, you might actually not be able to come up with an A is something, B is something. Like you might have more like a has to be equal to B, or C has to be equal to B over A, that kind of thing, depending on how many variables there are. How do the X and Y intercepts affect the number of solutions? So let's say that I have equation 1 and I have equation 2. and they have the same x and y intercepts. What does that mean about those two lines? Let's draw a picture to try and figure out what this means. So here's my coordinate plane. And here's my first equation in red. I've got some x-intercept here, some y-intercept here, and I'm going to draw my line. If I go to equation 2, and it has the same x and y intercepts, does that mean that the green line is the same line? Or is it possible to draw another line that has the same intercepts but is like a completely different line with a different slope? Well, I think you can see from a picture that if they have the same intercepts, they're going to have the same slope. They're going to have the same everything. This red line and this green line are the same line, right? So we can think about that too. Let's say that we have a different scenario where we have line 1 and line 2, and there's a looser condition. Let's say that they have the same x-intercept. Okay, that's the only clue that we have about them. They have the same x-intercept. We don't know about the y-intercept. Could be the same, could be different. So here's equation 1, has an x-intercept here. And here's equation 2, has an x-intercept here. So what do we know about the red line? Well, we don't really know much. Like, it could be like this, it could be like that, could even be like this. Like, we don't really know, right? Same with the green line. Like, the green line could be like anything, really, as long as it runs that way. Okay. Is it possible that they're the same line? It's possible. It doesn't tell us, though, but it is possible. So what you're seeing between the red and the green lines is that it is possible that they intersect right at this x-intercept. It is possible that they do. It is also possible that they are the same line. So there's two scenarios that are possible. Maybe they intersect at one point and there's only one solution between them. And maybe they're the same line and there's an infinite number of solutions between them. Is it possible, if the red and the green lines have the same x-intercept, for these to be parallel lines? The conclusion here is that it actually is not possible for these two lines to have zero solutions. Either there is one solution or there are infinite solutions, but there are not zero. Okay? That's going to be an important take-home message as you go later.